So I'm here today to talk to you about reactive architectures, and it's a relatively sort of gentle overview of what Reactive is about and why we wanted to use build architectures. I have multiple socials, don't we all? Because our home was vandalized. All right, who am I? I'm old. That's what the bit at the top says. For those of you who've never seen me before, I always emphasize the bit at the bottom, right? There's a danger that you think I am some kind of genius because I'm standing here. I'm not. I have a few grey hairs, which mean I've been doing things for a while. I've learned some things and I want to share them with you. You are equally capable of sharing things that you know with people who are newer to our industry than you are, and I encourage you to speak. Do we have any .NET developers in the room? Yay! So I work on an open source messaging framework and also acts as a command processor, which some people like Jimmy call a mediator, but Jimmy is wrong. But yeah, we're alternative to those. We're very friendly and very welcoming as an open source project, so please come and join us if you want to contribute. All right, a bit of preamble done. All right, so don't worry about it. I know you can't read the left. Well, if someone can read the left, you've got fantastic eyesight. Congratulations. But it's just, that is a copy of where you can go and find the Reactive Manifesto. The Reactive Manifesto was published in 2014. The main sort of author is Jonas Bonner, but there are some usual suspects in the list, like Eric Meyer and Greg Young, that you'll probably recognize. It's an architectural style. So what's an architectural style? Architectural styles are effectively the architectural equivalent of patterns. The most famous architectural style that many of you will probably know, some of you may even have read, is REST. Okay. Under the reactive approach, we want to write applications that react to events. Okay. And what the theory is that by reacting to events, we gain some additional properties. We gain the property that we can react to load, because we focus on scalability. We gain the property that we can react to failure, because they're more resilient. Don't worry, I'll explain all these properties and how they work. And we gain the property that we can react to, we are responsive to users, because we tend to stay up. Right? So these properties, responsive, resilient, elastic, and message-driven, are effectively the properties that we seek in a reactive architecture. You can go and find the actual document yourselves later and read it. Here's a simple version that's in nice big lettering, so we can all feel comfortable looking at it at sort of 10 past 12 on a Friday. We build applications that are message-driven, that is the means. And as a result of building message-driven applications, we gain two properties. Elasticity, so the ability in a sense to to scale out with new workers to react to load. Resilience, because we are message-driven, we have a buffer which contains our work. If we lose a component, we simply start a new one. And that result of being elastic, so we can basically respond to demand. Resilient, we stay up, means that we are considered to be responsive. Okay, and that's what we're going to show you how that works. Right. So that's a simple version. All right, so where does it come from? So reactive architectures are, in a sense, an expression of the principles of reactive programming. When we think about reactive programming, there are a number of contenders. The big ones you'll probably have heard of are data flow programming and actor models. And we'll also talk about flow-based programming. We probably won't focus on actor models in this talk. It's 45 minutes, so we don't have all the time in the world. But actor models are certainly a poster child for reactive systems. And reactive systems themselves are a series of principles and practices which are based on some of the ideas that reactive programming had, which allow us to build systems that have these properties. Okay. There's a core idea, which is everything flows and nothing stays, or flow. So reactive systems are concerned with flow, as opposed to kind of something that is very static, very fixed state. We're focused on flow the whole time. The Greek, I will try. Any Greek speakers in the audience? Oh, gosh. I do apologize for the massacre I'm about to commit to ancient Greek, but I think it's like tapanta re kai uden menai. Close? Oh, okay, never mind. Oh, ancient Greek philosophers turning in their graves. Okay, let's first of all, though, go back and we'll talk about objects. I'm sure most of us are aware of the world of object-oriented programming, but let's give ourselves a little bit of a recap. So we have classes, and classes have kind of private and public fields, okay? And they have private methods and they have public methods, okay? Great. And what the idea is that we essentially have some state, and we have behavior, which are operations on that state, and we collocate the two together. And even better, we can kind of hide the state so that people only interact with us by the operations, which feels nice and loosely coupled. I can change my data schemas internally quite successfully. You don't care, you just care that I continue to support the operations. We have some nice notions like base classes and composition, basically by containing other classes, right? As well as that, we do talk in object orientation about message passing, right? So if you have a program that Smalltalk's all about the message passing. But what they really mean is I'm making a call to this operation and passing it some parameters, right? So it is basically a procedure call. Dynamic dispatch, we can worry less about. That's the classic polymorphism that essentially you can interact with an interface or a base class, but you get the behavior on the concrete type. All right. Typically in object orientation, we end up with an architectural style called call and return. So call and return is pretty easy to understand. I have a main method. In my main method, I call another method. And that method may call another method, which calls another method. And we keep going down until things return and they bubble up, maybe to a lower level, maybe back eventually to main, and then we exit, right? So this notion is called call and return. There's a problem that emerges quite often with object orientation and call return, a kind of anti-pattern that creeps into our lives, and that's called the God object. So imagine, it's a bit of a trite example, but imagine in my main method, I'm effectively calling for my e-commerce site some kind of cart object. And imagine I want to perform some operations on the cart, like, telling you how much it's going to cost you to pay for this cart and whether you've got, Prime membership or whatever. One of the problems can be I make the call to the cart makes the call to the, this is food, so restaurant or the account. It makes the call to menu to check the prices of the items. We may call it to say, well, pay for the cart. We may even say, call the cart and say, turn yourself into an order. Right? And what's happened is cart's become the dreaded God object. Everything goes through cart. Everything deals with cart. Right? And so the change becomes pretty hard because it turns out any change you want to do probably involves changing cart. So when we built the first era of services, service-oriented architectures, as they were known, we tended to build in an object-oriented style. So web services description language, or WSDL, was kind of the language by which we described our services, and typically they had a set of operations that had an input message and an output message. But most cases, the way we implemented WSDL was basically by a remote procedure call syntax. By that we mean it looks as though to the programmer I'm making a local call, but I'm actually crawling out over the network or the wire to the far side. And the weapon of choice in the SOA era was SOAP, the Simple Object Access Protocol. Okay. Some of you may still have to deal with SOAP. I am sorry about that. Don Box, who created SOAP, retired to go and work on the Xbox. I think he'd seen too much. But we also have an endpoint, kind of an address the service lives at, typically a binding which says, hey, we're SOAP, or actually we're HTTP with XML, or whatever our service actually supports to do the work. Okay. So you can see we're all about the objects, right? We're all about the objects in the SOA era. There's a problem, right? It's the same problem we have with objects. And that problem is that typically what tends to then happen is we're making some call, and typically through some API gateway, and what happens is we may end up in the same world of, we're making procedure calls, so I call the cart, and the cart calls everything else internally, and in order to change anything, I have to go back and change cart. When we think about some of the era of microservices, the big thing, everyone, if you go and see Sam Newman talk about microservices, the thing Sam will keep, the phrase he will keep reusing is independent deployability. But the problem, of course, is quite often here, if payment decide we're going to support vouchers, and they basically want to release their support for customers using voucher codes, I've got to re-release cart, because I make calls to payment through cart. So I'm probably effectively adding my vouchers to the cart, which are then applied to the payment. So this independent deployability fades from us. And essentially what happens is we built a kind of call and return architectural style inside our service infrastructure, right? Typically, we tend to talk about this being a distributed monolith because the advantages that we'd hoped to gain from the independent deployability of our components seem elusively out of reach. The other option here that may also go wrong, just as a note, is somebody decides I'm going to create a public API that sits above my individual microservice APIs. Cart then just has CRUD-like API for cart, restaurant for restaurant, and all my actual business logic then drifts up into my API gateway. And that's even worse because now we don't even have our business logic inside a service. We have it in this amorphous layer we can't decide what to call. And maybe we misname it a BFF and feel really proud of ourselves. And generally, that's a bad idea. It's not a BFF. It's not a tailored interface for a given client. Right? So it's a problem. Feature envy is kind of this name for this idea that essentially you make too many calls to other things rather than doing work yourself. The other problem typically is in this model, particularly in the SOAP inheritance era that we had, you're typically doing RPC, right? And typically with RPC, what I'm saying is, well, you look as though you're making a local procedure call to this thing that's remote. There's a proxy, it marshals it into a network call. You've probably looked up via some mysterious key value store somewhere where the location effectively of the services that can deal with this call are. You send the call over the wire to them. There's basically some kind of stub at the other end, which effectively takes this work and essentially says, okay, I will marshal that into a local call on the server, and then vice versa to get the return back. And it seems like a very easy model for programmers to get into. And one of the attractions of SOA and SOAP in the web services era was this idea, we've made this really easy. Any engineer can do it. They know how to make procedure calls. They can make web service calls. What could possibly go wrong? Right. The problem, of course, is that network calls are not the same as calls in your local address space, because it turns out that things over the network can fail, and therefore you need to react quite differently towards making local calls, right? This is the fallacy about RPC, that it's made your life easier because all it's done is actually hide away from you. The problem is that you're making a network call and you need to deal with that. Now, in a sense, it's one of the reasons why HTTP is better than gRPC, because at least I'm aware quite often that I'm making an HTTP call. I haven't tried to hide that fact from the developer, so he's likely to take the relevant action. But it's also giving us a kind of temporal coupling, right? So the problem is if the menu service goes down here, I probably can't price my cart, right? And therefore, essentially, customers can't check out their orders. And it would be nice if that wasn't true, right? If actually each of these services was independent of each other, and if I actually lost one of my services because they had a bad afternoon, the rest of the stuff would kind of keep going, at least limping on for a while, so that we could continue to generate revenue on our site. Okay. So, having kind of described the problem, let's detour back into reactive and programming. And we'll explain how reactive programming works, and you'll begin to see why it's different as a model to the OO paradigm that we were very focused on for kind of SOA. Okay. So reactive programming is this idea that we can think of our software as a graph. And in this graph, there are arcs or edges, and there are nodes. So nodes are where we do computation. So we basically, run our computer program, and arcs are effectively how data moves between the nodes and then is transformed by passing through a node. So this idea of data and flow is key to understanding what data flow does, right? It flows data through a set of transformations. Now, an easy example that most of you probably know is the Unix command line, right? Unix command line tends to have this model, because everything is a file, of being able to basically pipe something from standard in through a program, and then out of that program to standard out, and you can kind of hook these things up in a chain such that you pipe stuff, through a grep, through a thing that does uppercasing of the word you've grepped, whatever, etc. Right? So we're all kind of familiar with that idea, and the key is that it's a pipeline of processing that I'm thinking about. My data moves down the wire, being processed at every step. Notice that the focus is different from OO, where we were focused on co-locating our data and our behavior. Here, we want the data to flow through our behavior. Why? Why is that better, right? Okay, so let's talk about coupling. Probably lots of you have done this at some point in your lives. Let's just refresh your memory. We like loose coupling. Loose coupling lets us make change easily, right? So when we talk about things like independent deployability, we're really talking about the loose coupling between components. I don't have to deploy you just because I have change. Tight coupling is the opposite, right? We are really intertwined and locked together. In order to basically me to release my code, you have to release your code. So worst kind of coupling is content coupling, and that's essentially we share code, right? If you make a change to the algorithm in your section, we have to make a change to the algorithm over here, right? I once worked in risk management software for mid-tier banks, and one of the problems there was, people would phone up and say, on this tab, it says the number is this. On this tab, it doesn't agree. It's got a different number. And the reason is because we had basically the same transformation in two different parts of code replicated twice, right? So common coupling is when we have globally shared state. Okay. Now, typically when we're thinking about programming models, that's basically the use of global variables. So if you're a C# dev, that's kind of static or whatever, right? But also what we included here is the idea of the big shared enterprise database, right? All of our software talks to the same database. We now have common coupling. We are coupled to shared data. Right? Generally, in modern service architectures, we really don't want to do the first two if we can, right? We accept some of the other, and we'll tell you what each one is. Control coupling is when essentially I effectively affect your behavior by passing you things and asking you to respond to those things. So that's your typical procedure call, is effectively control coupling, because I'm effectively passing you information and saying, please react to this information. So we're coupled by the structure of the information that I pass you. Okay. And we get control coupling in, say, when we send a message and that message is a command, right? So if we say, hey, price this basket, that is a command. I'm invoking an operation that you have, and essentially I'm passing you some parameters to it. So control coupling tends to exist in even the sort of best systems. Data coupling we'll do next. Data coupling is when effectively I am dependent of the schema of some data you share with me. Okay. So even in the sense of reactive programming, we have data coupling. So we will have to change if the schema changes. So it gets us into the world of versioning and that kind of thing. But it's about the lowest form of coupling we can have and still be useful. Beyond there is my computer lives in the basement of a dark room. It's not connected to the internet, and you can only use it by basically going and sitting in front of the terminal. It's pretty low coupling, but it's not much use to us for anything, right? Stamp coupling, which we missed out. So stamp coupling is where the data contains fields that I use and fields that I don't use, and I am coupled to the fields I don't use because I use the whole structure. In other words, I may have to change because the structure, the schema of the data changes, even though I don't use those pieces of data that have changed. And stamp coupling is, we try and work against that, right? But it's not a train wreck for coupling. All right. So in data flow programming, which is kind of Jack Dennis and others, the idea is I have this kind of node, which is a unit of computation. We can think of it quite often as a black box. My data flows in, it's transformed in some way, and it flows out the far side, right? And we think about basically these things, typically ports, which are input basically to my node and output from my node. And the way that it works is work comes in on this edge or arc. I instantiate a node in response to there being work, hence it being called reactive. I instantiate a node in response to there being work, I process it, and I push the answer out the far side. So those of you that use something like AWS Lambda or Azure Functions will be familiar with this idea of work arrives, I instantiate something to handle that work, and when there is no more work, I close that thing down, right? So that is a classic kind of reactive data flow model. Okay. So arcs or links can be buffered or not in data flow. If they are buffered, that allows us essentially to run the nodes in parallel, because what happens is while there is work, well, while I'm doing work, I just queue new work in the buffer. Okay. So the .NET developers amongst you will have access to a thing called the data flow programming library. It's often forgotten. It's very valuable. And it has these buffers for you that basically say, oh, I will do buffers between the nodes that you tell me about, and you can effectively have buffered input. Okay. You can be push or pull. So pull says this chain of nodes that performs whatever calculation I want to only exists when I pull from this end. So I say, give me the next one. Give me some more. So I'm effectively polling, right? Push says there's just a continuous stream of these things, and I simply just basically at some point wake up and say, okay, I'll start listening to the stream, and you take events as they're flying through towards you. Okay. So often that's some kind of events that you're witnessing, real-time events, weather reports and information, or even, I mean, the traditional model is when I move my mouse in a windowing system, I'm getting a stream of events fired, typically at the application under the hood, right? Classical Windows programming, where you wrote handlers that reacted to events, is just a reactive programming model, right? Okay. Node lifetime is I have work waiting, and I have work to do, and my lifetime is basically I am doing some work. And capacity, okay. If I don't have capacity downstream, typically this is an issue, this comes up when you have buffered output. If my buffer is full, I don't activate this node to process work of this buffer. And this is what we refer to as back pressure. Right. We say, we're all jammed up down here, let's not take on new work. And essentially that back pressure will flow upstream, stopping more work arriving as the buffers become full until whatever is at the front goes, hang on a minute, I better get the user to slow down. And that's when it issues a kind of like too many requests, please slow down, HTTP message, right? So that's back pressure. Okay. So we'll talk a little bit about flow-based programming. So Paul Morrison, who I feel has been unfairly forgotten by history a little bit, took these ideas in data flow programming and created something called flow-based programming. So in flow-based programming, we have our node, right? And we have basically some ports in and out, and we have our kind of arcs, which are called connectors in flow-based programming. And they are considered to be external to my node in flow-based programming, and they are always buffered. So they're always basically, we always do asynchronous work, basically, with flow-based programming. Interestingly enough, the reason I've drawn this as a hexagon is flow-based programming is a really early set of ideas, which is very similar to kind of ports and adapters or hexagonal architectures, because they say, internally, I don't know anything about the implementation of my connector. I just know there's a named port called in or out or whatever your name, usually it's much more descriptive of what you're doing, that I address from my code, and I say, hey, send this to that port. And therefore, effectively, I have a kind of ports and adapters model, right? So interestingly, kind of early kind of creation of a similar idea. And the data that travels down the wire, basically it's called an information packet, and it's just basically some data in a form that is yours to choose, right? Okay. Yep, okay. So, some slight differences. Packet lifetime is considered to be the buffer it's on. Generally, it's assumed that when you go through the import, you effectively end the lifetime of this packet. So you can think about that in modern messaging systems as I ACK the item on a queue and it's deleted, or I commit the offset in Kafka and we move on. We are done with that packet. and we put a new packet on the outside. Flow-based programming says, maybe you don't want to keep creating all these nodes, maybe they're expensive, maybe that's a cold start problem. So you know what? You can just sit there waiting for work, if you like, in flow-based programming. That does mean you need to think about, I need to to terminate this pipeline, I need a message that basically says, hey, shut yourself down. Right? So interestingly, Brighter effectively is a reactive programming model. We have a single thread, and you can basically scale by being asynchronous or scale the number of threads that you're running. And that single thread runs a message pump, which reads effectively off the messaging middleware that you're connecting it up to. And we just keep reading message of that middleware until essentially, when you want to shut us down, we insert a quit message as the next message into the buffer. So you process the current work, you finish the current work that you are processing, because it's single-threaded, you take the quit message off the queue, and essentially then we will terminate basically at that point, right? So that's a classic flow-based programming model. All right, so that's our node lifetime. And capacity, again, we can apply back pressure. We can say there is no room on the output queue, so we should apply back pressure and pause our work. Or in flow-based programming, you can shed load. So load shedding says, if there's no output buffer space, just drop the outgoing message. Don't send it. People may go at that point, why would I ever want to do that? That sounds terrible. But consider the example that comes from my current sort of place of employment, right? Working in the kind of food delivery business. If a courier is sending us signals, telling us where they're located, it's okay for us to drop some of those signals. The courier jumps on the map a bit, right? That's what's happening usually when you see your Bolt or whatever it is jumping on the map. We've just dropped some messages because the volume became too much, but we assume as a later one, which will give us more information so we can adjust at that point, right? So load shedding is the thing. All right. So flow-based programming I like because it answers some questions that otherwise people tend to struggle with when they're building message-based architectures. One of them is, what happens if in order for B to do its work, it needs some information that is generated in A? So let us assume, for example, that A is onboarding new restaurants for us to our takeaway food platform, and then in B, we want to grab the details of the restaurant's address to attach to our delivery request that's being dispatched to a courier. How do I get that information? Because it's passed through A, okay? So there are a couple of options. One of the most obvious options is essentially that I would ask A, right? So on my output port, my outlookup port, I put a message saying, hey, can you tell me basically the address of this restaurant? Goes to the import on this one. I, meantime, have to suspend that given workflow. So typically, I have to store some state with a correlation ID which says, okay, this work is being paused until we get a response. So I have to store some state to say where it was and what I should look up. A, which effectively onboarded our restaurants, has a whole lot of information about restaurants. It looks up the relevant address, puts it on a result with the correlation ID we sent it, comes back, we listen to it on the port down here, we effectively say, oh, look at the correlation ID, it's the answer to that one. We wake up the in-flight piece of work, read it from the database, we say, okay, here is the details you need, and then we pass out the finish request on the far side. Very simple model, and that works quite a lot. But a little bit, we'll end up doing the walk of shame, right? Because probably we'll keep asking for the same restaurant's address repeatedly. You know, McDonald's, KFC, these restaurants are popular, they get the vast plurality of orders, and so we're going to keep looking up the various McDonald's in your area. So it'd be nice to think about caching it maybe somehow. So we could think, well, maybe we could build a cache down here, and if we couldn't find it in the cache, we could look it up. But better is this model that effectively was flow-based programming identified. Nowadays, quite often called reference data, message pump, I've seen it called. The proper name is probably event carried state transfer. What we do instead is say, hey, whenever we add a new restaurant, we know that it's going to have to do a lookup. So we'll give it a local lookup table, and what we'll do is we'll listen to messages that come out of onboard restaurant, and we will basically have a little node that builds that table for us, and then it's the local copy basically that this one owns. It's read-only, right? We don't want to basically touch the read-write version because then we damage the independent deployability of this component, but this schema is ours, so we're only coupled to the data coming out of it. So we're coupled to the data, and we can effectively look up the information that we need at that time, right? So lookup tables were quite a common idea in flow-based programming years before we all got into ECST and decided that was a thing. All right, reactive systems. How does it all fit together? Okay, remember this thing, message-driven, elastic, resilient, responsive. Okay, so reactive systems are message-driven. We have a buffer, which is provided by the middleware, both the incoming message and the outgoing message. We use message passing so that essentially the two components don't have to be available simultaneously, and we can parallelize work. Right? That gives us some resilience to failure because essentially if this component goes down, work just queues. Right? Typically the model is going to be, hey, I've got some ports which effectively talk to middleware. Often I'm being asked to do something. We think about it as a command quite often. I will do something and I will produce results. The results might be facts saying, hey, I did this thing and you may care about it, or it may be another step in the workflow that I'm doing, right? We want to basically model these nodes around a verb-noun combination, place order, onboard restaurant, and typically we're trying to slice up our architecture into a series of processing steps that can usually be parallelized because that's the advantage of a reactive architecture. Okay, so as an example, I might have a checkout component and a take payment component, and what happens is some purchase comes in, we want to check it out, part of that is pricing, so we'll effectively talk to the pricing component. And we can parallelize basically requests talking to our external payment provider, and essentially these can just wait until a response comes back, and then we say that one is now priced. Okay. So as a reactive principle called coordinate data flow, you orchestrate on a continuous steady flow of information, focusing on division by behavior, not structure. So these are the different behaviors, and this is the data flowing down the line. Okay, I'll be brief with this because I talked about it in the talk the other day. Just watch the video, and I'm just conscious of time. I tend to think about these individual processing steps as autonomous components, and I quite often look towards Pat Helland's model for this. So effectively, you have explicit boundaries given to us by our ports, and what happens is when I receive a message, when I react, we tend to run what Pat calls an activity. An activity may interact with resources, so things in the business domain space where effectively we need to have control and manage that resource, or an activity state. So in other words, things to do with the running of a given state machine, like saying, hey, I've paused this workflow in order to get a response from another item. So two other principles: assert autonomy, effectively clearly define component boundaries, who owns what data and how the owners make it available, these ports. We isolate mutations, contain and isolate mutable state, which is these resources, right? So a typical model might be I get a purchase in, I do validate, price it, I request payment, right? So I pause my workflow, store some activity state. When the response comes back, the purchase is made. Okay, so overall, that would look a bit like this, right? I've got basically this flow, I've got purchase, I've got a price to take payment due, I come back with payment made, and I basically raise a new order saying, hey, they've paid for the basket, we've got an order. Okay, errors are just another flow, right? So if the card is refused, I simply change that into a payment refuse method, and checkout may do a request new card flow. Resilience. So work queues and a fault, we discussed that several times. Take payment can go down, the work will effectively just queue up. When take payment comes back up, we will effectively be able to process the outstanding work. We say this gives us bulkheads to failure, right? Because essentially the loss of an individual component doesn't stop us working. Again, typically what happens if we want to get some data from somebody else? So the bad world is we do some kind of HTTP GET to the pricing module. So here we're saying checkout wants to price the basket. So effectively it calls the pricing model. Typically the bad world is HTTP GET, because effectively we now temporarily coupled. Remember from the beginning, we're saying that synchronous communication, temporarily coupled. If pricing goes down, checkout breaks, right? So instead, we can do the same thing we did in flow-based programming. We either ask it, say, here is the contents of the cart, please can you price it, and it gives us back a price, or we use lookup data. So the pricing module, as it gets prices for things in the catalog, creates basically a message. We listen to that message and we build our own little cache of prices, and we just use that to do the pricing. Okay. Yeah, right. And that is essentially this idea of ECS2, right? And if we lose the pricing module, we may have to cope with the fact we've got some stale prices. That may be okay. Right? Typically, we make one or two choices, let the customer have it for a cheaper price, or two, just wait, have a version number stamp saying, what version of the catalog did the customer purchase from? If I haven't seen that yet, just wait on processing this one, in fact, you're applying back pressure until it becomes available. Okay. Reactive advises you to tailor consistency. So you can choose between eventual consistency, which is basically most of these models, right? And then being non-eventually consistent by using something like a get pricing model, depending upon your scenario. But you only get the resilience from choosing eventual consistency. This is important because of this. So generally the model in reactive systems is in the event of failure, we take the time-honored tradition of IT and we turn it on and off again, right? So the idea is to build components whose method of exiting is usually to crash. If you're hardcore, you don't give anyone a way of terminating your actual application. You say the only way of terminating this application is literally to kill the process. Because in a chaos monkey style approach, what it says is it forces developers to recognize that abnormal termination is the norm. And when you start up, you should do recovery. You should say, where was I? What was happening? What state was I in? I assume I'm not fresh and I crashed when I exited, right? So think about that, right? Well, I can show you on this diagram. If I've got a buffered work of queue, right, and this component crashes, then the work queues up for it, and then when it comes back up, it just starts processing the work again, right? So we're very resilient to individual failures. Back pressure, again, the idea effectively in some downstream resource, it may be the buffer, the outgoing queue, but it's much more likely to be, say, I can't access the database that I need or whatever right now. I can apply back pressure, right? And I can simply stop processing messages on the queue. So for example, quite a common strategy in Kafka, right? I have a whole lot of records in a stream. I come to the next record. I can't effectively, if I commit the offset, I'll skip over that one, right? So all I do is just keep retrying. It's called a blocking retry. And essentially I immediately apply back pressure because I'm no longer processing items in the queue. And I therefore wait to get stuff happen, right? We can also use a circuit breaker. A circuit breaker says, well, I'm going to do that blocking retry, but what I'll do is to try and figure out whether, I'll just do that indefinitely, and to figure out whether or not something is viable again, I'll test one through, try and process that. If it processes, I will take off I will stop blocking, right? Load shedding, which we discussed earlier, is just this idea that we can say, that's great, in the event the downstream resource is not available, I will simply discard the message and read the next one, right? So people often ask this question, because Kafka's not a queue, it's a stream. How do I deal with the fact that there's no re-queue in Kafka? Your answer is that you apply back pressure or you shed load. All right. Elasticity. So generally, reactive components are single-threaded. You can use async IO because effectively that's not uncommon. But just be wary if your async IO support doesn't respect your single thread, because the risk is that you will process messages out of the order you didn't expect if you're expecting the single thread to preserve your order. Writer, for example, is single-threaded on its async IO. It has its own synchronization context, as we call it, but you can screw with that, right? You can deliberately say, oh, use the thread pool, and that makes a mess. But you scale, so what you do is you scale out. So rather than increasing the number of threads, you just add a new instance. And that makes it much easier to work with things like Kubernetes. Often you're following 12-factor patterns. Those of you who don't know that, go look up 12-factor in terms of how you do app design. Okay. And that means if you get a fault, it's probably you've got some additional workers that can cope with the work anyway. All right, almost there. So, to recap, Message-driven applications are labeled elasticity. In other words, we can spin up new instances in order to cope with more load on our buffer. They are resilient because the buffering allows us to queue work in the event of failure, and as such are responsive because I can meet load and I can deal with faults. And that's what reactive architectures are all about. Thank you very much. Sorry I overran slightly. I'm happy to take a question or two, but I realize I'm standing between you and food, which is never the best idea. But if you want to walk up the front and just chat to me, or you can do a question if someone wants.
Yeah, I wanted to ask, when you have a context that builds a cache invalidation becomes a problem, right? Could you, from the sending context, build something like a read model, basically something that is outside of both, that is fueled by the one that is providing the messages, to have structured data to read from?
Yeah, when you're doing ECST, there are a few options, right? And generally, I think there's what's called reference data. It's read-only versions and immutable. It's not your inside data. It can have a different structure that you think is the public structure you want to share. You can, if you're using something web scale like Cosmos or Dynamo, you can actually create one that you can have multiple readers on, because it basically scales well enough to make that happen. But those get into, or even you can use S3 blobs of like with structured JSON data. So there are different ways of doing it depending on your actual circumstance.